Assalamu alaikum everyone. My name is Abdullah Haidar and today I will be discussing chapter 6 and chapter 7. So chapter 6 and chapter 7 are both about eigenvalues and eigenvectors. Not much difference in the chapter 7 concept, something a bit more in additional. And in chapter 7 we will also learn how to convert higher order equations to first order linear differential equations. So before we start, رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي رب زدني علما. The first thing you need to know in this chapter is this relation AV is equals to lambda V. And basically what this would mean is that this eigenvector V corresponds to eigenvector lambda, or this lambda eigenvalue can correspond to this eigenvector V. To test out this relation, we have our A, which is 5, 2, -6, -2, and our B is 2, 1. So if you find the dot product, you will get 5 times 2, 10, -6 times 1, -6. And 2 times 2 is 4, -2 times 1 is -2. So you'll be left with 4, 2. Okay? Now we compare this 4, 2. Compare this 4 to your lambda. So basically you need to find your lambda, and your V was already 2, 1. So based on this, we can deduce that our lambda is 2. And what we can say is, our conclusion is that this lambda is equals to 2 corresponds to our eigenvector of 2, 1. So lambda is equals to 2 corresponds to an eigenvector of 2, 1. This is all you need to know as the basics. And now we will move on to solving this question. Easiest way. Okay. So determine whether or not the following matrix is diagonalizable. If it is, find a matrix P and a diagonal matrix D such that A is equals to PD, P inverse. Forget of all of this for now. Forget whatever is written in the question for now. You have this matrix A is equals to 1. You basically have this matrix A 1, -1, 0, -1, 2, -1, 0, -1, 1. Forget what is written in this question for now. You look at the matrix. You have this matrix, and just don't look at the question for now. I know you will not get anything of this if you look at the question, but if you are to approach this question, the first step you need to do is find A minus lambda I. What do you mean by A minus lambda I? Is that you have this matrix A, you basically have the same matrix A, except you do 1 minus, you subtract everything on the main diagonal, you subtract all of these values by lambda. So when I say A minus lambda I, it means that you have to do 1 minus lambda here, 2 minus lambda here, 1 minus lambda here. So when we do that, 1 minus lambda and 2 minus lambda, 1 minus lambda, and write everything as it is. Write everything as it is. -1, 0, -1, -1, 0, -1. So this the first step is to find your A minus lambda I, which is basically subtracting these values on the main diagonal by lambda. So like you have 1, 2, 1 as your main diagonal. Basically, this diagonal goes to the right side. You minus these values by lambda. And now the next thing is find this determinant. Find the determinant of A minus lambda I. And it's basically how you used to find a determinant in chapter 3. You have 1 minus lambda. You have 1 minus lambda. And you cross out everything below and on the right side, so you're left with 2 minus lambda minus 1 minus 1, 1 minus lambda, and plus, oh no, the second was always supposed to be negative. It's supposed to be negative here. And you have this -1. Now you cross out everything uh, above and below this, and -1. See, this is gone, this is gone. So determinant, basically the minor, if you want to say it, -1, 0, -1, 1 minus 1 minus lambda, plus 0, and this is, I still write it, but this will anyways become 0. So 1, 0, 2 minus lambda minus 1. So after you do A minus lambda I, which is subtracting the lambda from the main diagonal, you find a determinant using the method in chapter 3, except like using this lambda. So you basically find the minors or cofactors. I'm not sure. I think it's supposed to be minors. So suppose so you find the minors of all of these values, and now you simplify. So you have 1 minus lambda. This will become 2 minus 3 lambda, I think. 2 times 1, 2, yeah, plus lambda square, and minus 1, so minus 1 times -1 is 1, so -1. We're done with this part. Plus 1, am I writing it to the matrix? So -1 times 1 is -1 plus lambda minus 0, so this will be as it is, and this will become 0. So we have 1 minus lambda square minus 3 lambda. To be honest, this is one of the most annoying steps you'll do in this question. Plus -1 plus lambda. And yeah, you simplify, expand. Lambda square minus 3 lambda plus 1 minus lambda cube plus 3 lambda square minus lambda plus -1 plus lambda. It's equal to now. And now finally you get minus lambda cube plus lambda square plus 4 lambda square minus lambda plus 1, so made plus 1, I guess. Minus lambda cube, 4 lambda square, minus 3 lambda minus lambda. This will become minus 4 lambda. So you have minus 3 lambda and minus lambda will become minus 4 lambda. It's very easy to make mistakes here. And this is added by -1 plus lambda. So now we get minus 3 lambda plus 4 lambda minus 4 plus 1 minus this is square minus 3 lambda is equals to 0. So we can factor this out. We can factor out lambda minus lambda squared plus 4 lambda minus 3 is equals to 0. Say your first lambda 1 is 0, and you can multiply the inside by negative lambda squared minus 4 lambda. This is lambda plus 3 is equals to 0. And here you get lambda 1 is equals to 1. Lambda, we already have lambda 1 is equals to 1, so this will be lambda 2 and lambda 3. Lambda 2 is 1, lambda 3 is 3. So these are basically your eigenvalues. So again, what you do is you do a minus lambda, you subtract all of these numbers. You subtract these numbers from the main diagonal by lambda, find a determinant, and then I forgot to write the step. Now you do the determinant of a minus lambda I is equals to 0. This will allow you, this equation will allow you to find the eigenvalues. Means making this equation equals to 0 and then finding the eigenvalues. So here you get lambda 1 is equals to 0, lambda 2 is equals to 1, and lambda 3 is equals to 3. So now we have our eigenvalues, and now our next job is to find our eigenvectors. So how to find our eigenvectors? So you use this equation a minus lambda I to find the eigenvalues, like using this equation and finding the determinant and then making this equals to 0. This is how you get the eigenvalues. But now I want to now find the eigenvectors. Now how to find the eigenvectors is you take each lambda, you basically take each lambda and substitute it here. A minus, so basically you have a minus lambda I, but instead what you'll do is now you substitute every lambda here in this and find the solution to the eigenvector. So basically what I mean is you had a minus lambda I, so a minus lambda I. So when you do this, this means that you go back to the main equation and you substitute lambda as 0. So after you find the eigenvalues, what you do is you put each eigenvalue in the main equation, in the main equation, and then you find the eigenvector using row reduction. So our first eigenvalue is 0, and our main equation was, so basically what I'll do is I'll substitute 0 everywhere for lambda. So 1 minus 0 gives me 1, and then there was a minus 1 and 0 here. Then minus 1, 2 minus 0, and minus 1. So 2 minus 0 is 2. So minus 1, 2, negative 1. Minus 1, 2, negative 1. And 0, negative 1. 1 minus 0 is 1. So 0, negative 1, 1. 0, negative 1, 1. All right. So now what we do is we row reduce this matrix. We row reduce the matrix like we used to do in chapter 3 and chapter 4. Here I can basically add row 1 to the second row. So this will give me 1 minus 1, 0. So 1 minus 1 is 0. negative 1 plus 2 is 1, and 0 minus 1, 0 minus 1 is minus 1. I write everything as it is, like this. And if I do the second row, if I multiply the second row by 1, by negative 1, if I multiply the second row by negative 1 and add it to row 3, basically if I make negative and negative here, so negative, so basically, well, there's no need to multiply by negative. My bad. So basically, you have your ones here. You have this one here. You have this one here. So you need to get rid of this one. You need to get rid of. You need to get rid of this negative one to make a 0 below the leading variable. So once you do that, 1 minus 1 0, 0 1 negative 1. So 1 minus 1 gives you 0. Minus 1 plus 1 gives you 0. 0 plus 0 gives you 0. And this is your reduced echelon matrix. This is your reduced echelon matrix. No, this is the echelon matrix because we still have. Basically, it's to be honest, it's your choice. If you want to get rid of this, if you want to make this a row reduced echelon matrix, means making everything, means basically getting zeros everywhere. You can. There's no requirement. But let's say I still want to find the row reduced echelon matrix. This is, as of now, an echelon. But if I want to do the row reduced echelon means I want to get a 0 here. And how I do this is minus. Why am I multiplying my negative? I'm going crazy. So if I add this row to this row, I'll get a 0 here means adding row 2 to row 1. So hence I will get 1. Now 1 minus 1 gives you 0. Minus 1 plus 0 gives you negative 1. 0, 0, 1 minus 1. 0, 1 minus 1. And 0, 0, 0. So this is your reduced echelon matrix. You have your leading ones, this and this, and you have nothing below or above them. So once you reduce this matrix, you need to find your lambda, you need to find your eigenvalue. So what you do is now a minus 0I, v is equals to 0, meaning assuming that this is your x, this is your y, this is your z, x minus z is equals to 0, and y minus z is equals to 0. And in most cases, you get x is equals to z and y is equals to z. Note that z is your free variable because you don't have a leading one here. You don't have a pivot column here. So we can say let z be your s. And in that case, this means that basically your eigenvalue will be in the form of x y z. So this means that our v1 is equals to now x y z. So since z is equals to s, we can say that s, then y is also y equals to z, which is also equals to s. So s, and z is also equals to s. You can take out the s, 1 1 1, So this is your eigenvalue. You ignore the free variable which you have, and your eigenvector. Your eigenvector is 1, 1, 1. So just a quick summary of what I did. After you find the eigenvalues, you substitute each eigenvalue into the main equation, and then you solve, and then you basically find the eigenvector using row reduction and making this equals to 0. So I row reduce this into this matrix, and I do x minus z equals to 0, y minus z equals to 0. And since z was a free variable, I took a parameter s. v1 is equals to s. I can take out the s, and then whatever I'm left as the vector itself is going to be my eigenvector. So this means that lambda is equals to 0 corresponds to this eigenvector. This is what I can say. If we got our lambda equals to 0 and v equals to 1, our job is far from done. This is done basically. Now we repeat the process for lambda 2 and lambda 3. So lambda 2 is equals to 1 means I'll substitute 1 in terms of in the place of lambda everywhere. So 1 minus 1 means 0. I'll write the main equation here again. A is equals to 1 minus lambda minus 1, 0, minus 1, 2 minus lambda, to make it a bit neat. So you have 1 minus lambda, negative 1, 0, minus 1, 2 minus lambda, negative 1, and 0, minus 1, 1 minus lambda. So this is your matrix A. And now we need to find our eigenvector corresponding to lambda is equals to 1, which was above here. Lambda 2 is equals to 1. So this means A minus lambda is equals to 1 means 1i. We need to find a matrix for this first. Means I'm substituting lambda is equals to 1 in this main equation. So 1 minus 1 gives me 0, negative 1, 0, minus 1, and then 2 minus 1 gives me 1, negative 1, 0, minus 1, and 0. So we are left with this matrix, and what I can now, I need to row reduce this. I need to row reduce this matrix. What I can do is first I can swap R1 and R2 by doing minus 1, 1, minus 1, 0, minus 1, 0, 0, minus 1, 0. And what I can do is minus 2R2 plus R3, basically canceling out this row. So minus 1, minus 1, 1, negative 1, 0, minus 1, 0, and getting this 0, 0, 0. So you might notice that if you have discrete eigenvalues, means you have lambda 1. So basically you have discrete eigenvalues. You have 0, 1, 3, and they're different. So basically you have 0, 1, 3. If you have different eigenvalues, then you will always have a row of at least one zeros in the reduced, meaning that, so basically these are distinct. Distinct means one I reduce the matrix, I'll get a row of all zeros only one time. So I'm getting here row of all zeros, and I got a row of all zeros here. So this is something important you need to know if you want to know if you're doing the question well or not. And what I can do is I can just write it as it is. Assume this is your x, y, z minus x plus y minus z is equals to 0. So now what we're doing is a minus I is equals to 0. A minus I multiplied by b. B is equals to 0. So we need to find this eigenvector like how we did above. We need to find this b. And this means making this matrix equals to 0, basically finding the solution space of this matrix. So x plus y minus equals to 0, and minus y is equals to 0. And this also means that y is equals to 0 if you multiply this. So basically you can multiply by negative on both sides, you get y equals to 0. This means minus x minus z is equals to 0, minus x is equals to z. Now, if you like do the proper way of row reduction, you'll get a 1 here, you get a 1 here, but this will always remain a free variable. So what you can say is let z is equals to s, and now your second eigenvector is going to be x, y, z, which is so minus x is equals to z means x is equals to minus z means minus s, and then y equals to 0, and that will be s. If you take out the s, you are left with minus 1, 0, 1. So your second eigenvector is going to be minus 1, 0, 1. Yeah. Well, what you can also do is, oh no, it's actually the same thing. It's actually the same thing. So now we found our eigenvector, which corresponds to lambda 0.621. So as I said, you put every eigenvalue in the main equation, which contains the lambda. You row reduce them, and based on your row reduction, you find your eigenvectors. And you can also write this as 1, 0, negative 1. There's no harm. You can always switch them. You can always switch them, but I like having positive 1 on the right, on the top. So now we need to find our eigenvector which corresponds to lambda 3 equals to 3. How do I do this? A minus 3i means I substitute 3 everywhere in this main equation. So I get 1 minus 3 is minus 2, minus 1, 0, minus 1, I should get negative 1, negative 1, and 0, minus 1, minus 2. Check if this is right. I'm just checking something. Yeah, so, yeah, that's right. So now what we need to do is find our row reduced echelon matrix. What I can do to this matrix is I can swap them. I can swap the first two rows. So swap R1, R2. I will get -1, -1, -1, -2, -1, 0, 0, -1, -2. And then I can do, then I can basically change the signs. Basically, what you can do is multiply the first row by -1 to just get rid of all this. Just get rid of all of these negative signs. You can basically multiply the row by -1 to get rid of the negatives. And now I can do minus 2R1 plus R2. I will get 1, 1, 1. This should be multiplied by +2. I'm going crazy, to be honest. If I multiply the first row by 2, I'll get a 0 here. So this is 2R1 plus R2. So 0, 1, 2, 0, -1, -2. Now I cannot get the mistake here. I can simply add row 2 to row 3. I will be left with 1, 1, 1, 0, 1, 2, 0, 0, 0. And as I said before, we had distinct eigenvalues. So it means we will always have a row of all zeros whenever we have distinct eigenvalues. So now I want to do a minus 3i multiplied by v is equals to 0. It's always better to write this. It's always good to write something like this, meaning x plus y plus z is equals to 0, and y plus 2z is equals to 0. And you should realize that we have a leading one here, we have a leading one here, and again here, here. So basically this is x, y, z. Z will be in a free variable, so let's say z is equals to s, meaning x minus x is equals to, your x is equals to minus y minus z. Here y is minus 2z, meaning y is equals to minus 2s, and here x will therefore become minus 2s minus s, which is minus 3s. So now you can write V3. This is a really long question, I know, but there's nothing we can do anything about it. Minus 3s minus 2s, and we have z like this. So s minus 3 minus 2 1. Wait, is this even right? I think there's a mistake here. Oh, so minus 2s, when you're substituting y here, it's supposed to be minus 2 minus, so 2s minus s. So this will give you x is equals to s. My bad. meaning like minus 2s minus s, so you get 2s minus s, which is s, so x is your s. Meaning your eigenvalue v equals to 3 is 1 minus 2, 1. This is your third eigenvalue. So now what we can write is for lambda 1 is equals to 0. Your eigenvector was 1, 1, 1 from above. Then lambda 2 is 1, means that the eigenvector corresponding to this eigenvalue is 1, 0, -1. And then you had lambda 3 is equals to 3, meaning your third eigenvector is going to be 1 minus 2, 1. Now, this is basically just half of the question. So basically, now we will do the question itself. Now we will do these questions itself. So determine whether or not the following matrix is diagnosable. Now, before I go that, just a quick summary. So from the beginning, what we did was a minus lambda I means subtracting lambda from the main diagonal, then finding the characteristic. So basically, this is called the characteristic equation from chapter 3, chapter 4, you might remember. Finding the eigenvalues and then substituting these eigenvalues into the main equation to get and after substitute them into the equation containing the lambda, you get this matrix, and then the row reducing them, making this equals to 0 will give you the eigenvectors. And once you're done with all of this, now you need to check if the matrix is diagonalizable. So what I mean by diagonalizable, it means you first find AP and PD to check if the matrix A, and it's talking about A by the way, determining whether or not the following matrix is diagonalizable means you find AP and PD. Now what is P and D first of all? I did not say what is P and D. Your matrix P, let me change the color first. Or should I just type it down? Your matrix P is the column matrix of eigenvectors. So matrix P is the column matrix of your eigenvectors, meaning that P is equals to means basically you substitute your eigenvectors as it is in this P as columns. So if I had V1 is 1, 1, 1, I would do 1, 1, 1. Then V2 was 1, 0, -1, 1, 0, -1. And V3 was 1, -1, so 1, -2, 1. This is your P, which is basically the column matrix of eigenvectors, and it's always preferred to write them in order, like how I did here. So V1 was the first column, V2 was the second column, V3 is the third column. It's always better to write them in order. And now what is matrix D? Matrix D is column matrix of eigenvalues. And this means that D is Now we had so basically what the purpose of the matrix D is to write these eigenvalues as a diagonal, meaning if you have 0, 1, 3, this means that 0, 1, 3, and zeros everywhere else. So 0, 0, 0, 0, 0, 0, 0. If I had something like 5, 8, 9, then your matrix D will simply be 5, 8, 9, then 0, 0, 0, 0, 0, 0. That's it. That's basically the main purpose of D is basically you write your eigenvalues in order, and again, I'm saying this because it's very important. Order matters a lot. You have lambda 1 is 0, so you have 0 here. You have this 0, then lambda 2 is 1, this, and lambda 3 is 3, this. And now you should also notice that this column corresponds to this column, this column corresponds to this column, this column corresponds to this column. So this is also really important. They should be matching. So basically this eigenvector should match this 0. This eigenvector should match this eigenvalue 1. This eigenvector should match this eigenvalue to 3. So now we found P and D. We are required to do AP is equals to PD. Means basically show that they're equal. Now, to be honest, I'm not going to do all of this matrix multiplication. You had A is here. A was basically 1, -1, 0, -1, 2, -1, 0, 1, 0, -1, 1. So basically, it's kind of debated. It's like a big debate of whether you should do all of this multiplication. I was with Dr. Khalid last semester, and he said you should show the steps of multiplying A by P and then P by D. You need to show all of that to get the full marks. Otherwise, you will lose marks. Basically, I did not. Basically, what I did was I just wrote AP is equal to PD, and I lost 2 marks. So basically, you need to show this matrix multiplication. 1 minus 1, 0, minus 1, 2 minus 1, 0, minus 1, 1, and then multiply this by P, which is 1, 1, 1, 1, 0, -2, 1 minus 1, 1, and then equals to PD means 1, 1, 1, 1, 0, -2, 1 minus 1, 1, and multiply this by D as well. So I was with Dr. Khalid, and he said that once you do all of this, you need to show like the working of all of these multiplication of rows and columns and all that. Just to save time, I won't be doing this, but in the exam you have to. In the exam you have to show all of this matrix multiplication working. I will just write that AP is 0, 1, 3, then 0, 0, -6, 0, -1, 3. If you feel like you cannot do all the steps, there's no time, just do it on the calculator. And on the right side, when you do the multiplication, you will also get 0, 1, 3, 0, 0, -6, 0, -1, 3. So you can say that. So after you multiply both matrices by both like multiply them by each other, you say since AP is equals to PD, then you have to say this. A is equals to P D P inverse. So basically, since AP is equals to PD, then A is equals to PDP inverse. This is something you must write. And then since the eigenvectors are linearly independent. What I mean by independent is you have these eigenvectors, and linear independent means you cannot write one vector in terms of another vector. So this and this are linearly independent. This and this are linearly independent. This vector and this vector is also linearly independent. So when you say that since the eigenvectors are linearly independent, your matrix A is diagonalizable. So these two statements are important. And you need to say that A is equals to PDP inverse, and since the eigenvectors are linearly independent, matrix A is diagonalizable. So basically, we've answered this question. We found the matrix P, we found a diagonal matrix D, and we showed that. So you don't need to show this. You don't need to start multiplying matrices for this all over again. What we need to show is P is invertible. How to show P is invertible? There are two ways. I'll just do the easiest way, which is you find a determinant. To show that P has an inverse, invertible means it has an inverse. You simply find the determinant of P, means you find the determinant of this matrix 1, 1, 1, 1, 0, -2, and 1, -1, 1. And when you find the determinant of this matrix, you'll get determinant of P is equals to -6, which is not equals to 0. Hence, P has an inverse and is invertible. So if the determinant is not equal to 0, it has an inverse and it's not it is invertible. If it is 0, no inverse means not invertible. And that is the whole question. That is the whole question. I think this took 40 minutes or something, maybe more than 40 minutes. You need to be really quick in the exam. A very quick summary. First step is A minus lambda I. You substitute, not substitute, you subtract the main diagonal by lambda. You find the determinant of A minus lambda I. You find this characteristic equation. You find lambda 1, lambda 2, lambda 3. These are distinct, means you will get, so in the row reduction, you'll get a row of 1, 0. You'll get at least one row of all zeros, so basically 0, 0, zeros. And so after getting your eigenvalues, you find the eigenvectors using this A minus 0, I, A minus 3I, A minus 1I. You find all of that, you find all of the eigenvectors. And your matrix P will be the column matrix of eigenvectors. So this. Your matrix D will be the column matrix of eigenvalues 0, 1, 3 as in the diagonals. And to show that they are diagonalizable, you do AP is equals to PD. You show the whole working of this, by the way, not only the final answer. And you show that they're equal since AP is equals to PD is equals to P dP inverse. And since the eigenvectors are linearly independent, matrix A is diagonalizable. And to show that P is invertible, you find a determinant of P. If it's not equal to 0, then it has an inverse and is invertible. That is chapter 6. That is your chapter 6. Only this one question, and it always comes in the final exact same format. So now we'll move on to chapter 7. And the first 80% of the question is literally the same thing. you're given this determinant without looking at this question. You have this matrix A, and as I said before, you do minus lambda on the main diagonal, like minus lambda here, minus lambda here, minus lambda here. You do all this and you find the determinant of this exactly how I did. You just you do using the minors. You get this equation, and you can also simplify this. You can simplify into this, and you get lambda is equals to 1 and 2, 2. But note here that you have repeated eigen. You have repeated eigenvalues. Now, I will tell you what does the repeated eigenvalues change like how does it change the method or something. But first of all, let's focus on lambda is equals to 1. So this means you're basically substituting lambda equals to 1 here. So putting lambda is equals to 1 in this equation, and you're row reducing to find the your eigenvector. So A minus I is minus 2, 3, 3. So minus 1 minus lambda is negative 2, 3 minus 1 is 2. So you should get 2, 2 here as well. 2, 2, yes, correct. And once you row reduce this, you do A minus I, V is equals to 0. So, and this is your, Z is your free variable once again here. Z is equals to S. So basically you get X minus 3Z is equals to 0. X is equals to 3S in the case. And Y minus Z is equals to 0. Y is equals to Z. Second, so basically you can write this as 3S and y is equal to z, which is z is equal to s, and s, you take out the s, which is 3, 1, 1. This is how you get your eigenvector. So up till now, everything is normal. For lambda 1, so lambda is equal to 2. A minus 2 lambda means you're substituting 2 in this matrix. And no, this is where things get different. If you have repeated eigenvalues, and this also applies to chapter 6. This applies to both chapter 6 and chapter 7. 6, 7. Lemuel likes doing this. So if I divide the first row by 3, I will get minus 1, 1, 1, minus 1, 1, 1, minus 1, 1, 1. So using the row operations, I can literally get all zeros in these two rows. You have two rows of all zeros. So just a quick comparison. If you have lambda is equals to 1, so in the characteristic equation, we got lambda is equals to 1, 2, 2. This one is by itself, meaning you have a row of one row from zeros. But 2 and 2, these are repeated. 2 and 2 are repeated means when you have repeated eigenvalues, when you have repeated eigenvalues, 2 was repeated twice means you'll get a row, you'll get this row and this row all of zeros. This also means that for this eigenvalue you'll get two eigenvectors, so means you will get eigenvector v2 and v3 for the same lambda. So basically our v1 corresponds to lambda 1, and since since the 2 was repeated here, we will have V2 and V3 corresponding to the same eigenvalue. So when we do the RREF, as I said before, you have repeated, so you'll have 2 rows of full zeros. And if I want to do A minus 2I multiply this by V is equals to 0, meaning your X minus Y minus Z is equals to 0. Note that this is your only leading one. You don't have a leading one here. You don't have a leading one here. Meaning, because of this column and this column, assume that Y is equals to S, Z is equals to T. So X is equals to Y plus Z, meaning X is equals to S plus T. Then Y is equals to S, Z is equals to T. You can write this as S plus T, S, T. And like chapter 6, chapter 4, you can separate them. So S 110 plus T 101. And the vectors itself are going to be your eigen vectors, and these are independent because you cannot get V3 from V2 and you cannot get V2 from V3. These are like independent. So just to show you, so basically this is exactly like chapter 6, except the only difference was you have repeated eigenvalues, and for these repeated eigenvalues, always remember that you basically had two which is repeated, meaning you will have 2 eigenvectors and you will have 2 rows of full zeros, you'll have 2 free variables, and that's the only difference. So meaning that lambda 1 corresponding to V1 is what was V1? 311. Your V1 was 311. And then when you had lambda 2, you had a V2 and a V3. So V2 was 110 and your V3 was 101. If they ask you, is the matrix diagonalizable? So what you can say is V1, V2, V3 are independent, and then you find AP, PD, and like P is basically, P in this case would be 311, which is basically like the column matrix of the eigenvectors. So 311, 110, 101, this would be your P. And then D was, as I said, the column matrix of your eigenvalues. So your eigenvalues were 1, 2, 2. So 1, 2, 2, and then zeros everywhere else. So this method applies to chapter 6 as well. So till now, for the chapter 7 part, this is all you have to do. Show that 2 is an eigenvalue of the matrix A and solve the following system of equations. So here it did not ask you to check diagonalizable. You did not have to show AP6 PD. So a chapter 7 question looks like when they give you an initial condition, which is x of 0 is equals to b, meaning x0 is equals to this vector 1, 5, 3. Whenever you get an initial condition, this means that you're answering a chapter 7 question. Unless not specified, you don't have to do AP is equals to PD. You don't have to find PD. You just need to know that this eigenvalue gives you this eigenvector, this eigenvalue gives you these 2 eigenvectors. So now we need to find our equation, which is in terms of x of t. And how to do this is your x of t will be in the form of c1 c1 e power lambda t v1 plus So basically, in the general form, x of t is Cn e power lambda n t Vn. Basically, depends on how many eigenvalues, eigenvectors you have. So this is something you need to memorize because this is different from chapter 6. C1 e power lambda 1 t V1 plus C2 e power lambda 2 V2 and since we had two vectors for the same eigenvalue, we will write C3 e power lambda 2 V3. So basically, you need to memorize this formula. C1, which is basically C1, C2, C3 are your constants. C1, C2, C3, and then e power lambda 1 t V1, lambda 2 V2, e power lambda 2 V3. If you had distinct eigenvalues like the one which was in this question, if you had distinct eigenvalues, and this would simply be x of t is equals to C1. What were the eigenvalues here? So you had the eigenvalues in the first question was 0, 1, 3. So C1 e power again? Yeah. So C1 e power lambda t, lambda was 0, t, and then your V1. What was your V1 here? Leave it. So V1 plus C2, just to give you a general idea of what it looks like if you have distinct eigenvalues. So C1 e power 0 t V1 plus C2 e power 1 t V2 plus C3 e power 3 t multiplied by your vector 3. So this is how it looks like if you have distinct eigenvalues. But in this question, we have repeated eigenvalues, so we'll have to write V3, C3 for the same eigenvalue here. Now we substitute. Our initial condition was x of 0 is 1, 5, 3. What does this mean is, and this is supposed to be t here, lambda 2t and lambda 2t. Basically, what this means is 1, 5, 3 is equal to, and then you substitute 0 everywhere in terms of t. If I substitute, let me first write the whole thing. Let me first write the whole thing properly. Our x of t is C1. Now our first lambda was e power 1, so e power t. What is our V1? 311. 311 plus. Now you have C2, your lambda 2 was 2. And what is your V2? Your V2 is 110. 110 plus your C3. What was the C3? C3 e power, and this is supposed to be 2 years. So C3 e power 3t again. No, 2t. 2 is repeated, so lambda 2 e power 2t, and your V3 is 101. Now, what I mean by x0 is equals to 10153, I put 153 on the left side, and I substitute t is equals to 0 for everywhere. So t is equals to 0 means this becomes 1, this becomes 1, this becomes 1. So I'm left with C1, 311, plus C2 110 plus C3 and 101. And now we need to find our C1, C2, C3. We can do this using the method of chapter 3. You might remember chapter 3, finding the solution to your equation. So basically treat it like you're solving this equation. Assume that this was your x, y, z, x, y, z, x, y, z. You're basically solving this system of solutions. And what you will do is you'll basically put this in a matrix. So assume that this is your so basically you're forming your augmented matrix. Augmented matrix and then solving this matrix. So you had 3 1 1 1 1 0 1 0 1 and 1 5 3. So basically you need to find the solution C1 C2 C3. You can solve this by doing R or AF, or if you can use Kramer's rule. Basically, what you want to do is you want to solve this system of equations. To save time, I'll just write here 3x plus y plus z is equals to 1, x plus y is equals to 5, x plus z is equals to 3. You can use Kramer's rule, you can use the row reduced echelon matrix. You can use any of these methods to solve this equation. And since we're dealing with C1, C2, C3s in this question, we will write it as 3C1 plus 3 plus C2 plus C3 is equals to 1. C1 plus C2 is equals to 5. C1 plus C3 is equals to 3. Whichever way you want to solve this equation, just to save time, I will write C1 is -7. C2 is 12, C3 is 10. So when you get your C1, C2, C3 using any of your favorite methods, you can finally write your solution x of t. So we have x of t is C1, which is -7, e power t multiplied by your v1, which is 311, and C2 is 12, so plus 12 e power 2t, 12 e power 2t, 12 e power 2t, and then multiply this by your v2, 110, 110, plus now I have 10, same eigenvalue e power 2t, and your vector was 101, 101. Now what you can also do is you can combine them into a single matrix. Dr. Khalid especially likes this method. So you can write this as minus 21 e power t, and then 12. And then you can basically just combine them into one single matrix as your answer. So minus 7 plus 3 minus 7 times 3 makes 1. The 12 plus 10 gives you 22 e power 2t, and then minus 7. To be honest, you can leave your answer as it is, like this. But if you want to keep it as a matrix, you can multiply minus 7e power t, and then this will be 12e power 2t, and minus 7e power t, 12 times 0, 0, 10 times 1 is 10. So both methods are correct. This is how you solve this question. This is chapter 7. So once again, just a quick summary. You have x prime is equals to ax. Whenever you see x prime is equals to ax and x0 is equals to b, first what you do is you find all of your eigenvalues. You find all of your eigenvectors. Once you're done with all of that, and note that since we have repeated eigenvalues, meaning that for lambda is equals to, we'll have two eigenvectors, we'll have two rows of zeros, we'll have two free variables. So watch out for that. Once you read this step, you don't have to find P and D in this question. I was just explaining, and your solution will be in the form of x of t is equals to c1 e power lambda 1 t v1 plus c2 e power lambda 2 t v2 plus c3 e power lambda 2 v3. Substitute everything, and you have another system of equations to solve. When you solve this, you'll get your c's, and this is simply your final answer. I know this is really, really tedious. Hope so basically your hope should be that chapter 6 and chapter 7 should be merged into one question so that you don't have to repeat many things. And that is all about the eigenvalues, eigenvectors. Now, this concept, which is transforming higher order equations into system of first order equations. I'll go through this very, very quickly. Why? Because in the quiz, you can expect this kind of question in the quiz, but in the final, unlikely. Basically, what you have to do is you need to convert this higher order equation into a system of first order equation. Dr. Khalid would not bring this question, but it could come in the quiz, but unlikely in the final. I still have to teach you how to solve this equation. So how to do this question? You first identify what is the highest order. So you have x prime, x prime, x triple prime. X triple prime means the order is, the highest order is 3. Why? Because you have x triple prime. This means that you will have to find x1, x2, and x3. You need to know your x1, x2, x3. Why? Because the order is 3. Let's say I had the highest order was 2, means I would have to do x1 and x2. If the order was 1, then I only have to do x1. But for the purpose of this question, the highest order is 3, means always and always, this means finding x1, x2, x3. You need 3 new variables. Now, x1 is always equals to x. x2 will be always equals to x prime, and x3 will be always equals to x double prime. Now, if you're feeling confused, don't worry about this. Even I was confused in the beginning. So as I said before, you identify your order, which is 3, and then you write x1, x2, x3, and always you begin with x on the right side. So you basically, it is always guaranteed that your x1 is always going to be x. Then x2 is always going to be the next derivative of this x. So this is x power x. So this has no derivative. Your x2 will be the first derivative of this x, and then your x3 will be the second derivative of the previous one, which is x double prime. And our requirement is a system of first order equations. So what I'm looking for is, I'm looking for x1 prime, I'm looking for x2 prime, I'm looking for x3 prime. This is what I want to find as my final answer. So just a quick recap. Order is 3 means we need 3 variables of x, x1, x2, x3. x1, we will always set it as x. x2 will be the next derivative, and x3 will be the next derivative of these x's. So we know what is our x1, x2, x3. Now what is our x1 prime? Our x1 prime, is this derivative, which is x prime. Then what is our x2 prime? x2 prime is our next derivative of this x. It is x2 prime. What is our x3 prime is the next derivative of this one, which is x triple prime. I know for sure that you're feeling confused over here as what's going on. I will explain one more time because I know very well that you can understand. So you have order of 3. Order of 3 means x1, x2, x3. Now, know that x1 is always going to be x. Your x2 will be the next order of this x, which is x prime. And then your x3 will be in the next order of your previous x, which was, so this is x prime. You will be increasing this by 1. You know what is your x1, x2, x3 equals to? Now you can find the derivative. So your x1 prime is basically x prime. Your x2 prime is x double prime. Your x3 prime is x triple prime. This kind of remember what is going on. And now we have our x1 prime, x2 prime, x3 prime. Our main purpose, I use this now. I use this as a reference. So you've identified all of this. We first delete we have here. Okay. So once you get your x1 prime, x2 prime, x3 prime, you compare with what you have over here. x1 prime is equals to x prime. What is your x prime equals to on the left side? You have this x prime here and this x prime here. So this gives you x2. Now you can write x1 prime is equals to x2. Now x2 prime is x double prime. You have this x double prime. You have this x double prime. This belongs to your x3. So what I'll write is x2 prime is equals to x3. Now I want my x3 prime. Here x3 prime is basically this equation, literally like this equation. What I mean by this is basically your x3 prime is your x triple prime. So I will rearrange this first equation to give me x triple prime. So x triple prime is x double prime, x double prime, x double prime minus 3t x prime minus 5x plus ln t. So now we substitute our x double prime was our x double prime was x3. So this means we'll have x3 here. X double prime represents our x3 minus 3t. Now our x prime is represented by x2. x2. And our minus 5x, our x, assume this, so this is our x, and this is represented by x1. So minus 5x1, and you write plus ln t as it is. So now you can write your system of equations. x1 prime is your x2, x2 prime was your x3, x3 prime is basically now writing this equation in terms of x triple prime, and you get x3 minus 3t x2 minus 5x1 plus ln t. This is your final answer to this equation. I know this looks kind of tricky. I guess you'll get used to it. But let's check our understanding using this now. If you're still confused, don't worry about this. This might make things clear. You want to transform this system of equations into first order linear system. So the order of this is 2. The order of the system, and this time you have y. Don't worry about this. This time you have y, but just know that you have your highest order for x double prime is 2. So this means you'll have x1 and x2. You have y double prime. Orders 2 means you will have y1 and y2. Now same step as before. Our x1 will be our x2 will be our x prime. Now I want to find my x1 prime, and I want to find my x2 prime. Now x1 prime is basically x prime. I do the derivative of this both sides, and I get x1 prime is equal to x prime. And now this x prime matches x2, means my x1 prime is equal to x prime, and this x prime matches leads me to x2. This might make things more clear, and same for the y as well. You have y1 prime, y1 is equals to y, y2 is equals to y prime. So if I want to find my y1 prime, this will basically be y prime, and this y prime leads me to y2. Hopefully now things should start becoming clear. Now how to find our x2 prime? This is basically same as rearranging this equation. X double prime is equals to 5x plus 4y. And then y double prime is equals to minus 4x plus 5y. So we rewrite this, but so x double prime is 5x plus 4y. Our x here refers to x1. So you can write this as 5x1 plus 4y. Now that we have a y here, this y leads to y1. 5x1 plus 4y1. Should this be negative? There's a positive here. This becomes negative. So this was supposed to be 5x minus 4y. My bad. And hence this should be 5x minus 4y. So we found our x1 prime, x2 prime. We need to find our y2 prime. y2 prime is the same as our y2 prime. Y2 prime means basically your double derivative of y, and this means that y2 prime is this equation, but using our x1 and x2, basically x1 and y1. So minus 4 x refers to x1 plus 5y plus 5y. This y over here refers to y1. And now we can form our system of equations. We basically want x1 prime, x2 prime, y1 prime, y2 prime. So you can write this as x2 5x. Wait, why am I writing this like this? So you want to find your x1 prime is equals to x2 prime is equals to y1 prime is equals to y2 prime is equals to. So in this case, we have x2 from here. Our y1 prime is from here, y2 from here. And we can write our x prime as we found them. 5x1 minus 4y1 minus 4x1 plus 5y1. If you don't understand, like if you still don't understand despite my efforts, there's nothing I can do about this. I explain this concept as well as I can. If you still don't understand this part, I know my explanation is kind of rusty. And if you still don't understand, you can ask your professor or watch some YouTube video. All right, so now I will be discussing about complex eigenvalues. So basically, this is a question: x prime is equals to ax, and your a is 0, minus 2, 2, 0. And we want to solve this question. This is the chapter 7 question, but this time you will get complex eigenvalues, and you need to know how to deal with that. So if I do a minus lambda I, first if I do a minus lambda, I'll get the matrix minus lambda, minus lambda, minus 2, 2, yeah, that's it. So if I find a determinant, this would be not lambda, not k. Lambda square plus 4. And if I make this equals to 0, lambda square plus 4 is equals to 0. I get lambda is equals to 2i, lambda 1 is 2i, and lambda 2 is minus 2i. So you can see here that these lambdas are complex values. And to be honest, there's really not much difference in dealing with them. What you will do now is, when you have lambda 1 and lambda 2, when you have 2i and minus 2i, it's always preferred to take the positive one only. So you can say that the second lambda, which is minus 2i, will not be used in the next steps. So it's always easier to deal with the positive lambda value. So when I do a minus 2i, a minus 2i, I means I substitute 2i in this equation, in this matrix. So minus 2i minus 2, 2, I think this would be 2i. Check. Yeah. Minus, yeah. So this will be minus minus 2i minus 2 minus 2i. So now I think what I can do is, if I want a row reduced echelon matrix, I can divide the first row by um, 1 over minus 1 over 2i power 1, and I will get 1 so you do minus 2 over 2i, this is minus 1 over I. How do you how do you do this? I'm thinking. So you get minus 1 over I. If I multiply by the conjugate, minus I minus I get I over minus 1 squared, which is minus I. So here you get 1 minus I and 2 minus 2i. If you do minus 2r1 minus 2r1 plus r2, then you'll get 1 minus I 0 0. So you're basically left with this. What you can do is x minus, so basically now we're doing a minus 2i big I v is equals to 0. So this means that x minus yi is equals to 0. X is equals to yi, and let's take let y be 1, means x is equals to I. X equals to I, y equals to 1 means our eigenvector is going to be I1. This is going to be our eigenvector. So this means that our solution is going to be x of t is equals to, now since this is only, since we're considering only one eigenvalue and one eigenvector, it's going to be t e power 2i, and we have this vector I1. Now there are some things like you need to know. This is supposed to be e power 2it, by the way, e power 2it. You need to know that whenever you have e power how to explain it? There was that identity. That was an identity. I'm just trying to, I'm just going to say is, if you have e power it, let's say you have e power it, then it'll be cosine t plus I sine t. Just know that if you have e power it, this will be equals to cosine t plus I sine t. But you have a 2 here. So this means that e power 2it will be equal to cosine 2t plus I sine 2t. So basically what you can think of is, if you have e power it, I know by itself cosine t plus I sine t. E power 2 it is equals to cosine 2t plus I sine 2t. So basically, whatever coefficient you have over here is going to be inside the cosine sine functions. So like if I have e power 3it, this will be cosine 3t plus I sine 3t. I kind of forgot what kind of rule is this or identity, but you need to know this identity basically. if you have any number, if you have a coefficient of I which is greater than 1, so like if you have 1 here, you'll have a coefficient, you'll have 1 here, 1 here. If you have 2 here, means cosine 2 plus I sine 2t. So you kind of, so you get what I mean. And what I'll do is C, and then you have I1. You have to multiply this by cosine 2t plus I sine 2t. And when you multiply this vector, you get, so basically you have x of t is I multiplied by cosine. So if you do I cosine 2t plus I sine 2t, and we're doing matrix multiplication here. Cosine 2t plus I sine 2t. All right. So if I expand the I towards the inside, I get x of t is I cosine 2t, and if I have I times I, that becomes -1 minus sine 2t, and the below part and the part below stay the same. Cosine 2t plus I sine 2t. So this is your x of t, and now you know that in complex numbers you have real parts, imaginary parts. So now what you can do is x of t is equals to, now you can split them into real parts and imaginary parts. So basically this is your real part, sine minus sine 2t and cosine t. What you can do is you can introduce new c's this time. Since we want to keep it real plus imaginary part, what you can do is C1, and this will be a real part. A real part is minus sine 2t cosine 2t plus, now you will want to do it based on the imaginary part now. And usually we do not include the letter I. We usually don't include the letter I when it comes to these problems. So C2, ignore the Y. Cosine 2t sine 2t. So now we have our initial condition, which was x of 0, x0 is equals to 1, 0. So 1, 0 is equals to, so basically x of 0. If I substitute, so C1, 0, this become 1, plus C2, 0, this becomes 1, 0. So basically, what does this mean? I'm running out of space, by the way. Oh, C1 times 0, 0. C2, so basically, you have this 1. From this, you can see that your C2 is 1. And if you consider the bottom part, zero is equals to C1 times 1 plus C2 times 0. So your so your, 1 second. 1, 6. Okay. So your C1 is going to be 0. So you have C2 is equals to 1 and C1 is equals to 0. What you can do now is your final x of t equation. Your final x of t equation is going to be, now since C1 is 0, this whole thing goes off. So C2, which is 1, so 1 times cosine 2t sine 2t, and that's it. That's this question.